In this podcast, we're going to talk about calorimetry and calculations, and also how it relates to energy diagrams. So what calorimetry is studying energy changes either in chemical reactions or in just heat transfer. And it's a method to measure heat changes in any process. A calorimeter is a device that allows you to measure changes in temperature, and this is the simplest type of calorimeter, which is a coffee cup calorimeter, which is at constant pressure, and it usually involves a foam cup with a thermometer in it and sometimes some sort of insulated stopper. And it's nice if you can have a way to stir it, but sometimes you just stir it with a thermometer. And the equation that we use is heat, which is Q, is mc delta T, where delta T is the change in temperature, and C is the heat capacity of the substance, and it's usually in water, so it's going to usually be the heat capacity of water. There's also something called a bomb calorimeter, and that's at constant volume. So it is a sealed container, and it's made of metal, so it doesn't expand. And a substance is added, and it's ignited or burned. And when it burns, it heats up the solution, which can be water or oil or whatever it's made of. And the change in temperature allows you to measure how much heat comes from the substance. So here again, the equation is Q, which is heat, is the calorimeter of constant times the change in temperature. And the calorimeter constant has to be determined experimentally for each calorimeter, and that's usually given in the problem. So if we're talking about heats of reaction, which is delta H of Rxn, or heat of solution, which is delta H of solution, what is H? And H stands for enthalpy, which is the internal energy or thermal energy of a system. We actually cannot measure H all by itself because we have to have a reference point. So instead, we always measure change in enthalpy, or delta H, which is the change in internal energy, and that's going to be at constant pressure. So if we have the heat of a reaction, which means the heat that happens when we mix two things together and it forms a reaction, the change that takes place, delta H of reaction is Q of the surroundings. So if the reaction gives off energy, then the surroundings are going to increase in temperature, and we can measure that heat, Q. And if a reaction absorbs energy, then the surroundings are going to lose heat or temperature, go down in temperature, and we can measure that. So Q is the heat released or absorbed by the surroundings, which we usually can measure. It's usually in water, and we can measure the temperature change. And the units for delta H are joules or kilojoules. And keep in mind that they can also be in calories, but we are going to use joules in this unit. So if the delta H of reaction is positive delta H, then the reaction is endothermic and energy is absorbed by the system from the surroundings, and the surroundings are usually the solution. If the delta H is negative, what this means is that the reaction is exothermic and energy is released by the system to the surroundings, so the surroundings are usually going to increase in temperature. So we can draw energy diagrams. For the first case, endothermic means energy is absorbed, and what that means is here's the delta H along this axis, and this is the reactants, or the starting point, and because energy is absorbed, we are going to end up at a higher delta H, so delta H is going to be positive. So we draw a curve for that, And there's always going to be some sort of activation energy that we have to get over, so some sort of hill. And A, this distance here, is the energy that has to be added for the reaction to go, to break the bonds in the reactants. And B, this distance here, is the energy that is released when the new bonds are formed. So energy in is A, and energy out, energy that is released, is B. This distance C is the difference between them. So it's A minus B, and because A is larger than B, delta H is going to be positive. And that's true for an endothermic reaction. The energy diagram, if delta H is negative, is going to start out higher and end up lower. Again, we have to put energy in to make it happen, so there has to be some sort of activation energy or hill to get over. This distance in the activation energy is A, which is the energy that we have to add. And B is the energy that is released at the end of the reaction, or when the products are formed. And just like before, the distance C is A minus B, and because in this case we get more energy back, B, than we put in, delta H is going to be negative. So the delta H solution is actually exactly the same thing, except it's what we call it when, instead of doing a reaction, we add a solid to a solution, usually water, to a liquid, usually water, and it dissolves. And sometimes it is exothermic, and sometimes it is endothermic. So if we write this as a reaction, we've got a solid, AB, and then we put it into water, and it dissolves, and we write that as AB aqueous. And if energy is absorbed by the system from the surroundings, which are water, then it's going to be a positive delta H. If, on the other hand, when we add our solid to water, if energy is released and the temperature goes up, then the delta H is going to be negative. It's exactly the same as a reaction, but it's just a different process. And then keep in mind, if energy is absorbed, it has to come from the surroundings. So the temperature of the water is going to decrease. If energy is released, it's going to go into the surroundings, and the temperature of the water is going to increase. So we're going to attach some math to this. If we have a reaction, which is, in this case, the decomposition of aluminum oxide, and the balanced equation is 2 moles of aluminum oxide decomposes and makes 4 moles of aluminum plus 3 moles of oxygen gas. The change in enthalpy for this process is positive 3,352 kilojoules. And keep in mind that this is kilojoules, not joules, and that is going to be for every 2 moles of aluminum oxide because of the 2 right here. So is this reaction exothermic or endothermic? Because the delta H is positive, it is endothermic. And because it is endothermic, it means energy has to be absorbed by the system from the surroundings. So what that means is that heat must be added, so we can add heat to our equation. It doesn't have to balance or anything, but that means that heat is a reactant and we have to add heat to make it happen. So adding some math to this, how much heat must be added, it's going to be in kilojoules, to decompose 25 grams of aluminum. So here we're given our reactant in grams, and the delta H is always going to be per mole, or in this case per 2 moles. So we're going to have to convert aluminum oxide from grams, 25 grams, convert that to moles. So the information that we're given is that the delta H is 3252, that should be a 3 right there, 3352 per 2 moles, again, because of the 2 here. And then converting aluminum oxide, 25 grams, divided by its molar mass, gives us 0.245 moles of aluminum oxide. So then if we combine those two things, we have the number of moles of aluminum oxide and 3252 kilojoules for every 2 moles. And then we plug that into a calculator and get 398.4 kilojoules. That's the amount of energy that has to be added to decompose 25 grams of aluminum oxide. So the next example, it's a solution. In this case, we're adding sodium acetate, solid, to water, and it is dissolving and making an aqueous solution. And the delta H for this process is negative 17.3 kilojoules, and that is per mole, per 1 mole, because of the 1 here. Because this is an equation that is exactly 1 mole of sodium acetate. So is this reaction, or process, sorry, exothermic or endothermic? Because it is a negative delta H, it is going to be exothermic. So therefore, adding sodium acetate to water is going to increase the temperature of the surroundings because it is exothermic, so energy is released in this process. So how much heat would be released by adding 10 grams of sodium acetate to water? So again, the 10 grams, we're going to have to convert that to moles because we have our delta H in kilojoules per mole. So 10 grams of sodium acetate divided by its molar mass gives us 0.122 moles of sodium acetate. And now that we have the moles, and we know it is 17.3 kilojoules per mole, do the math and we get 2.11 kilojoules released. If we wanted it in joules, we'd multiply by 1,000, which is 2,110, and because it is negative, that energy is going to be released. So now we're going to combine it with some calorimetry. So let's say we took our 10 grams from question C and we put it into 50 grams of water. So the energy that was released, the energy that we calculated here, this 2,110 joules, that amount of energy is going to go into the 50 grams of water. So this is our Q, 2110. And we're adding it to 50 grams of water. And what we can do is we can solve for the change in temperature of the water. So the energy that is released is Q. The Q that it's absorbed is 2110 joules. We're using joules because our heat capacity is always going to be in joules. So that's why I converted this kilojoules to joules in this case. And that is equal to mass times the heat capacity of water, because it's in water, times delta T. And in this case, we know the mass, we know the heat capacity of water, we know the Q, we know the heat, and we're going to solve for the change in temperature. This change in temperature is going to be positive because the heat is going to be released and the water is going to get warmer. So mass is 50, heat capacity is 4.18. We're going to solve for the change in temperature. So plug that into our equation. Solving for delta T here, we get 8.2 Celsius. It says to calculate the final temperature, and we know the change in temperature. We have to know the initial temperature of the water. If the initial temperature was 20 degrees, which is room temperature, we would add 8.2 degrees to that and get 28 degrees. So it would increase by 8.2 degrees.